do this again. Okay, we are recording. Yep, there's that little dot there. Okay, I wanted to start off today. We're considering the simple harmonic motion again, and we can just think of the mass on the spring for a while. But if you've got this spring here, it's attached up at the top to something firm, and you've got a mass hanging on it. And the way we did it in class to make it bounce, we got the thing where it was at an equilibrium position, and then you lifted the mass up above there a little bit and let go. Now, just before you let go, where was the energy of that system? And there was no kinetic energy because the mass was at rest. There was potential energy. Okay? Now, one of the things it had was gravitational potential energy, and another is some spring potential energy when you raised it. Now, it turns out that the gravitational potential energy will drop out of the equation if you redefine the spring potential energy to be stretched by the amount that the weight of this thing stretches it. And they may go through that in the textbook, I'm not sure. But what it lets us do is ignore gravitational potential energy and think, okay, I raised the mass above the equilibrium position for the mass spring system, and there will be potential energy stored in the spring, and we can call it 1/2 kx squared, where x is the new position of the thing. You can think of that as x if you want to. Anyway, when it's up there and the mass is at rest, the energy is going to be 1/2 kx squared, as long as you think of x as the distance you raised it above the equilibrium position. Now, the mass drops down from there, and when it gets back to the equilibrium position, there will not be, oh, actually, we could call that x, we could call that 1/2 ka squared, because that's going to end up being the amplitude of the motion. So that's our initial energy. Now you let it drop down. When it gets down to the equilibrium position, it no longer has any spring potential energy because the spring is back to its equilibrium position. And this is a little bit complicated by having the gravitation in there, but as I said, it drops out. Anyway, what you've got there is kinetic energy, and you'd end up with E at equilibrium equaling 1/2 mv squared. So there's that. And then it goes down a distance x or a distance a below the equilibrium position. And when you're down there at the bottom, you again have spring potential energy of an amount 1/2 ka squared, where it stops for a moment at the bottom of the motion, so there's no kinetic. So we've got this interplay of energy going on throughout the motion of the thing. And if we make a graph of the position versus a function of time, and this is supposed to look like a sine wave, when it's at the extreme of the motion, if I make a PE and a KE graph, it's got potential energy right here, but it has no kinetic energy. Okay. When we get to this spot here, I should be putting the graphs down at the bottom, it's got kinetic energy, but the spring is at equilibrium, so we don't have any spring energy anymore. And the height of this thing is exactly the same as the height of that thing. Halfway between, it'd have a mixture of the two. And then you get down to here, and it stops instantaneously. The slope goes to 0 right at the bottom of here. This is an x versus t graph. Okay, so you get down to here, and again, you've got potential energy, no kinetic energy. Okay? And then you get back to here and you're fully kinetic energy and so forth. And you keep having energy transfer from potential energy into kinetic energy gradually. It's not a digital thing like what I've drawn here. So halfway between, you've got a mixture. Halfway between here and here, you've got a mixture. And it just keeps transferring back and forth between those two types of energy. Well, let's see what we can write for this stuff. And I've got a problem where actually I wrote the energy of this system at any given time looking like this. 1/2 mv squared plus 1/2 kx squared. And the x in this case is the distance away from equilibrium. And as long as we don't have any energy lost to friction, this is a constant. Well, can you take a derivative of this thing? Okay. Well, let's do that. Now, keep in mind, v is a function of time, and x is a function of time. So it's v of t and x of t. So if I took a derivative with respect to time of this, if there's no friction and no energy lost to air resistance or anything, that's going to be 0 because it doesn't change in time. Well, what's that mean here? I can take a derivative. The mass is constant. The spring constant is constant. That's why we call it a spring constant. Let's see, taking a derivative of the first term, I'd have 1/2 m, and then I take the derivative of this v squared. And v is actually a function of t, but first I'd get 2v, and then I'd get dv dt. Is that the chain rule? I can't remember. Something like that. One of you math whizzes could tell me that. And then I'd add the last term. I'd start off with the 1/2 k. It's constant. It doesn't matter. Take a derivative of x with respect to time, and I'd get 2x and then dx dt. So what's this going to look like? Let's see. Well, 1/2 times 2, I can do that in my head. It's equal to, what is it equal to? It's equal to 1. Anyway, I'd have mv. What's dv dt? That's a. Okay. Yeah, ma. Let's see, plus, what else have I got here? I've got 1/2 times 2 again. I've got kx. What is dv dt or dx dt? It's v, right? And so that's what I have, and this is supposed to equal 0. Well, I can factor all this stuff out of here or factor a v out of the two sides, and I'll have v times ma plus kx, and that's equal to 0. So either v is 0 or this thing is equal to 0. Well, I think this thing can be 0. If v is non-zero, you can divide it out. If it ever is 0, then you're at the extremes of the motion. But here's what you get out of here. You get ma plus kx is equal to 0, or ma equals minus kx. That's the expression for the spin force. It's minus kx, and ma is that's the net force that's acting on something. So this ends up giving us Newton's second law for the spring situation by taking a derivative of this thing. Kind of an abstract thing to be doing, but that's okay. It's harmless enough. That's one of the example problems that I usually use for the second day of this thing. But I'll show you Something else that comes out of here, if we remember that x is equal to, for this situation, it's equal to a cosine of omega t plus phi, and that's our most general expression for x when we've got this simple harmonic simple harmonic motion going on. Let's see. We also had an expression for v, which we get by taking the derivative of this, and it ends up being minus omega a sine of omega t plus phi. Okay, so we have that. Now, let's take the energy equation that we have, E equal 1/2 kx squared. And this isn't going to be just at some particular instant. This will be at all possible times. If we stop the motion at some instant, there will be some distance x away from the equilibrium position, so we could have some potential energy. And at that instant, there would be some kinetic energy as well, so we'd have a 1/2 mv squared. But let's take the expressions for v and x and plug them in here for x and v. So I'd get 1/2 k times a cosine of omega t plus phi quantity squared, that's squared, plus 1/2 m times minus omega a sine of omega t plus phi squared. Well, when you square a negative, you get a positive. Kinetic energy is always positive, so because it depends on the square of the speed. Anyway, here I would get 1/2 k a squared times the cosine squared of omega t plus phi plus 1/2 m. Well, when I square this, I'd get omega squared a squared sine squared of omega t plus phi. And that's it for there. Okay, I can almost simplify this thing, but first I need to do something about m omega squared. Remember what omega is? It's the square root of k over m. So when I square it, I'll get k over m for omega squared. And so this expression is going to change into 1/2 ka squared cosine squared of omega t plus phi plus 1/2. I'm just going to look at m omega squared is equal to m times k over m. It's just k. Okay, so this would be 1/2 ka squared sine squared of omega t plus phi. And we stopped or studied the motion of this stuff, this object, at an instant in time when they both have the same value of omega t plus phi. And so I can factor out the 1/2 ka squared. And left inside, I'll have cosine squared of omega t plus phi. Some of you know the punchline already, plus sine squared of omega t plus phi. And that's one of the first trig identities you learn. I think that's called the Pythagorean identity, if I remember right. Anyway, that's one. So the energy in this bouncing system, which we already kind of looked at, is 1/2 ka squared. And that's going to make it possible for us to solve a bunch of different problems by knowing that at any given time, 1/2 kx squared plus 1/2 mv squared will always equal 1/2 ka squared. So, let's see how we can use that in some problems. So that's a handy thing to know. In this simple harmonic motion, we've got something like that. Now that's for a spring, but section 14.4 of your textbook looks at different types of oscillatory motion. Pendulums is one of the things they look at, a torsional pendulum. Lots of different situations similar to that. And it works. Anyway, this is a problem that I don't know why I had it on my list of problems for the first day, because the way to do this problem is to take energy into consideration. It's complicated otherwise. Anyway, we have a 0.500 kilogram glider. I think we've seen a few of those already. Attached to the end of an ideal spring that has this force constant, undergoes simple harmonic motion with that amplitude. Not much, 0.04 meters. That's only 4 centimeters, which is, I don't know where my ruler is, but it's like maybe that much. Not very much. Calculate the maximum speed of the glider, the speed of the glider when it's at that particular point, and the magnitude of the maximum acceleration of the glider. All of these things we can figure out, but the way to do it is to use that energy equation. And so they tell us what the amplitude of motion is. We can figure out the maximum speed of the glider from that, because here's the thing. The total energy in the system is 1/2 Ka squared. Oh, by the way, got to say this. We've got somebody coming to replace a door, and we may hear some door replacement noises from time to time, like that sound. Anyway, ignore it. So here's the total energy of the system. That will equal the kinetic energy of the mass as it's passing through the equilibrium point. So we can say that's equal to 1/2 mv max squared. All right, well, let's see. The maximum speed of the glider. I know what the amplitude is. I know what the spring constant is. I know what the mass is. It's just a matter of solving that thing. And so, and actually, well, knock out the 1/2s here. I'll get Ka squared equals mv squared, or v max squared. V max squared is going to be K over m a squared. K over m is omega squared. So this is actually just omega squared a squared. And V max, the maximum speed, is just omega times a. Well, remember the expression for the speed at a given time? V is minus, now this is actually the velocity at a given time. It's minus omega a sine of kx minus omega t. That's the velocity. Well, the maximum value of the sine function is 1. And so the maximum speed, if you take the absolute value of this, is just going to be omega a times 1. So we didn't have to do this much work to figure it out. So anyway, V max, I can just take that square root of K, which is 450 newtons per meter, divided by 0.500. Now that's 2 sig figs here, 2 sig figs there. We've got 3 on that, but we can keep 2 sig figs anyway. Times the amplitude, which is 0.040 meters. This one we can do in our heads, believe it or not. Let's see, 0.500 kilograms. If you remember that a Newton per meter is a kilogram per second squared, what's inside the square root has units of 1 over second squared. So when you take the square root, it'll give you 1 over seconds times meters is meters per second. So that'll work out nicely. And anyway, 450 divided by 0.5 is 450 times 2, which is 900. Square root of that's 30. So you'd have 30 times 0.04 meters, except let's use a calculator because I don't trust myself, but I'm pretty sure that's right. I get not much, 1.2 meters per second. So not so terribly impressive, but it's a little dinky thing bouncing back and forth. Okay, how about the speed of the glider when it is at x equals minus 0.015 meters? Well, at any given time, energy is going to be 1/2 k a squared. That's going to equal 1/2 kx squared plus 1/2 mv squared. Okay, we're interested in the speed when x is 0.015 meters. It's going to get squared here, so that'll turn it positive. But I can just use this thing to figure it out at any intermediate point. So first of all, divide out by the 1/2, get rid of those, and you can say ka squared minus ax squared is going to be mv squared, or let's see, v divided, I'm going to do 2 algebra steps at once. My favorite trick is k over m times, actually 3, a squared minus x squared. And I want to take the square root of that whole thing. Okay, so lots of algebra steps at once there. At any rate, we will have k over m, that's the 450 newtons per meter divided by 0.500 kilograms. And we'll be down to 2 sig figs because that's all we have there. And then times the amplitude is 0.040 meters. And I'm subtracting away 0.015 meters minus 0.015 meters, but it's okay because I'm going to square it. Okay, unit-wise, what's this going to give us? Again, newtons per meter is the same as kilograms per second squared. Divide by kilograms and you get 1 over second squared. These will have units of meters squared, so meters squared per second squared when you take the square root gets you to meters per second. And if it's not less than that, I'll know that I've made a mistake. So, okay, that sounded like a Sawzall taking nails off to me. Sorry about the noise. They were going to come Saturday morning and had an opening in their schedule. Okay, anyway, I get 1.1 meters per second for that. But the key part was this was how I did it. I used conservation of energy. The total energy will equal the sum of the potential and kinetic at any given time. All right. Another question, the magnitude of the maximum acceleration of the glider. I'm going to do that the easy way. And let me show you what that'll be. If I take the time derivative of this thing, I would get the acceleration is minus omega squared a cosine of, whoa, this isn't right. Did you guys notice that? We're going to have that for the argument of a sine and cosine function be soon, but it should be omega t plus phi is what we should have up there. What I wrote down is the equation of a traveling wave, which is the next unit. Man, it's interesting how stuff gets lodged in your brain. But anyway, we'll have cosine of omega t plus phi. You were probably wondering, what in the world is this? But the maximum value of the cosine function is 1, just like the sine function, which means the maximum acceleration of the acceleration is just omega squared a. So this is a max. So to get that a max, I just go equals omega squared a, and omega squared, omega is the square root of k over m. Omega squared is k over m. So k over m times a. So it's just going to be the 450 newtons per meter divided by 0.500 kilograms times, let's see, the amplitude again was 0.040 meters. Okay. So A max, not so terrible to calculate. This is 900 again. And I get 36 meters per second squared. Okay, this problem has a lot of parts, but it's having us explore just about everything you can about this. So it's a nice example in that respect. D is to find out the acceleration of the glider at x equals minus 0.015 meters. So the time when it had that velocity we were figuring out. But here's how you do that. The acceleration is going to be the force divided by the mass. Excuse me. The force is minus kx because it's a spring. The mass is what we know the mass to be. And the k over x is the same as this thing. It's that 900 per second squared is what the units end up being. And so we just have to multiply that by that distance x. So anyway, I would have minus 450 newtons per meter divided by 0.500 kilograms times x, which is minus 0.015 meters. And I'm keeping track of my signs here because this spring force is a restoring force. So if you compress the spring in the positive direction, the spring force is back in the negative direction, as is the acceleration. But in this case, we have the spring, I guess, stretched in the negative direction, but the restoring force will be back in the positive direction, and we're going to get a positive acceleration here. So A is equal to whatever that ends up being. Okay, and it's about 13.5. meters per second squared. So again, this combination of units gives me per second squared. So that's why I end up with that. Okay, and then finally, the total mechanical energy of the glider at any point. Well, I can figure out that a bunch of ways. I can use 1/2 Ka squared. I can use 1/2 mv max squared, which I now know. Let's just do the 1/2 Ka squared. So I'd have 1/2, well, Ka squared is equal to 1/2 times the 450 newtons per meter times A, which is 0.040 meters squared. Unit-wise, I'll have newtons per meter times meters squared, which will actually give me Newton meters, which is joules. So the E total, just plug and chug again, and I get 0. Not a whole lot of energy, 0.36 joules. Okay, I don't know if I pointed this out before, but if you imagine the little 100-gram masses that you used in the lab on Tuesday, if you drop one of those 100-gram masses from a height of 1 meter onto your foot, it doesn't hurt much. It's not very massive. Don't do this with the 1 kilogram masses, you'd break a toe. But one of those little 100-gram masses dropped from a distance of about a meter, a little over a meter, ends up being an energy of 1 joule. So this is only 36 hundredths of a joule, not so much. Okay. Any questions on these? I know I'm kind of racing through them, or it feels like it is to me. This, yeah, it's kind of the last one I have. Although, let's see, I did pick up another one here somewhere. Yeah, we can do that other one too. Anyway, a simple harmonic oscillator sounds like a mass on a spring. Another noisy operation, whatever it is. Consists of a block of mass, 2.09 kilograms. Numbers aren't so nice this time. It's probably one I made up. Attached to a spring of force constant 105 newtons per meter. When t is 1.47 seconds, the position and velocity of the block are x equals 0.129 meters and v equals 3.14 or 415 meters per second. What is the amplitude of the oscillation? Okay, well, I'm going to do this with energy considerations. And remember that 1/2 Ka squared will equal 1/2 mv squared plus 1/2 kx squared. Now, this is true at every instant of the mass bouncing up and down on the spring or back and forth. It's always true. This is the total energy of the system. And so I'm after the amplitude, knowing the speed at some particular time, although the time actually doesn't matter. But knowing how fast the thing is going at some instant in time and where it is at that time, I can figure out what the amplitude has to be. So if I multiply this through by 2, I would get Ka squared equals mv squared plus kx squared, divide by k, and I will get a squared equals m over k times v squared. Whoops, talking and writing at the same time, times v squared plus just plain x squared. So now it's just a matter of plugging the stuff in. What's the equation of motion? That's going to be a little trickier, but let's see what we can do here. We know the mass, 2.09 kilograms. We know the spring, 105 newtons per meter. And we know that at this instant, it's going 3.415 meters per second. That gets squared. Plus this particular thing, x is 0.129 meters. So that was it. We just had to use the energy consideration thing here to be able to figure that out. Okay. Well, I guess I'll just plug the numbers in. And I get, let's see, I can keep 3 sig figs on this. Oh, that's a squared that I just figured out, which is 0.249 meters squared. Is that going to be meters squared? Let's take a look at this thing. A Newton per meter is the same as a kilogram per second squared. So this divided by that ends up giving me seconds squared. And if I multiply seconds squared times meters squared per second squared, I'll get just plain meters squared. So I'll have meters squared plus meters squared. Yes, I do have meters squared there. So A is the square root of that number, which is 0.499. So just about half a meter is the amplitude of the motion. Okay, now here's something that's kind of tricky. What is the equation of motion for this thing? And let's see. Well, in general, x is equal to a cosine of omega t plus phi. The omega is easy. That's the square root of k over m, and we've got enough information for that. We know what a happens to be, but what about phi? How are we going to figure that out? Well, they tell us it's at t equals 1.47 seconds. The velocity and the thing happened to be that. So we should be able to figure that out from there. But before I do that, I want to figure out the period of oscillation for this thing, because it may be that this is more than one period after it started. And if that's the case, we can end up with a larger than accurate value for phi. Not that it'll make any difference, because adding factors of 2 pi under this thing don't have any effect on the argument because it repeats. But anyway, the period is 1 over the frequency, and the frequency, well, let's go over here. Omega is the square root of k over m. That's 2 pi times the frequency, that's equal to the square root of k over m. So the frequency is 1 over 2 pi times the square root of k over m. The period is 2 pi times the square root of m over k. And maybe you don't quite understand my justification for doing this, but I'm just curious what the period is compared to that. So I'll have 2 pi times the square root of 2.09 kilograms divided by 105 newtons per meter. And again, that's a kilogram per second squared. Divide a kilogram by that, and I'll end up with seconds squared. When I take a square root, I get seconds. So yes, I'll have the period in seconds. So 2 pi times the square root of 2.09 divided by... Okay, and I get that the period is 0.886 seconds. And so that's how long that happens to be. Well, this 1.4 seconds is past that. Okay, so it's gone through one complete cycle and it's partway through another one. And so I'm going to subtract that period from this time because we get exactly the same values for X and V one period before. Whereas if I did that whole thing, I'd end up with a somewhat larger than expected value for phi. I'd actually end up with one that's 2 pi larger than we need. So at 1.47 seconds minus 0. I'll call it 0.87 seconds, and I'm going to be down to two significant figures no matter what. So 1.47 minus 0.87, I don't feel like doing that in my head. I get, that doesn't make sense to me. 886. Did I plug something in wrong? Oh, that's 0.89 is what it is. Okay, that's why. I get 0.58 seconds. X and V are the same as given. If I was to rewrite this problem, I'd give you 0.580 seconds for this instead of 1.47 seconds. But that's all right. All right. So what we can say is X at that time is equal to A cosine of omega t plus phi. A, we know that's the amplitude, which we figured out up there, 0.499 meters. Omega is the square root of k over m. I don't think we actually calculated that here. T is the 0.58 seconds we just figured out. And so we'll know everything except phi in this result. So I'm going to write it out. Actually, I'll figure out omega once and for all. Maybe I'd done that. I don't know. Okay, for omega, I get 7.09, and that is radians per second, or just seconds to the minus one. So that's omega. So our equation of motion at that time, we know that x is 0.129 meters. So 0.129 meters is going to equal the A, 0.499 meters, times the cosine of omega, which is 7.09 radians per second, times the 0.58 seconds plus phi. Okay. All right. Well, if I divide this by that, I'll get something dimensionless. Lots of complications on these things. I can keep 3 sig figs so far. 0.259 equals the cosine of this stuff, which I'm not going to bother to rewrite. It's exactly that, so stick it down in there. Anyway, take the inverse cosine of both sides. The cosine to the -1 of 0.259. By the way, in this unit, I'm having to put my calculator in radians mode. In fact, I'd better do that because I haven't done it yet, but I don't know that I've just been doing algebra. Fix psi, yeah, I'm in degrees. So, okay, now I'm back in radians. Inverse cosine of that thing is going to equal, I can multiply these two, 7.09 times 0.58, which is 4.1 plus phi. Okay, good. That's less than 2 pi. Anyway, what I'll end up with up here, the inverse cosine of that is 1.3 sig figs. I do have 3. Well, it doesn't matter. 1.31 radians equals 4.1 radians plus phi, or phi is going to equal that other stuff, minus 4.1. So minus 2.8. And I've only got 2 sigs on that. All right, now it asked me for the equation of motion. Okay, I can now write it out. X is equal to A, the amplitude, which is 0.499 meters, times the cosine of omega times t. Omega t is going to be our only variable, so 7.09 radians per second. And I know some of these things, when we actually do the work, times t minus 2.8 radians. So we figured out our first phase constant for one of these problems. And that's it. So position and velocity at 0.0 seconds. Well, the position, I just have to set t equal to 0, and I'll have the cosine of minus 2.8 radians times that. So x of 0 is going to equal 0.499 meters times the cosine of minus 2.8 radians. And my calculator can handle that. I'm only going to have 2 significant figures when I'm done, but minus And I would get minus 0.47 meters. So almost its full extension, just 3 centimeters away from that maximum extension, but in the negative direction. So that's something I can figure out. V of 0 will equal minus omega A sine of omega t plus phi, but omega t is 0, so omega t is 0, and it'll be the sine of phi, which is minus 2.8 radians. And I expect this to be positive because this is negative out front, but the sign of a negative argument is negative. Actually, how did I get that there? Oh, I guess just because it's 2.8 radians. Actually, I'm not positive about this. The sign could be positive or negative out there. I'm not sure. But I'd have to plug in all the numbers. And then we'll stop there, I think, because this has been a pretty full day of problem solving. Omega was, wherever it went, 7.09 radians per second times A, which was 0.499 meters, times the sine of minus 2.8 radians. Yeah, I don't know if it'll be positive or negative. I can't do that one in my head very well. Actually, I think this may be negative, but we'll see. Um, Yeah, this is negative, so this comes out positive. It's 1.1, actually it's 1.2 is all I can keep on there. Meters per second, because that's a meter times a radian per second. Radian's just a placeholder word, so it's meters per second. Okay, that was a complicated problem, another one with lots of parts. So yeah, but the last two problems I did have about everything you might want to wish for in a complicated, or might be asked for in a complicated simple harmonic motion problem. Now that's a contradiction in terms. A complicated simple harmonic motion problem, but you might print those problems off and give them a shot by yourself because they're pretty good practice in figuring out all of these things. So try that. Let's see. Later today, I hope to have the video from this session and the video from the earlier session posted up so you can access them from Canvas. And then I'll also publish the homework assignment in the lab as well, so you can see those. And tomorrow, let's see, tomorrow's Friday. Oh, I also need to have you fill out a survey that has your name on it for when you could do labs next week, because all I saw was X's and I don't know who can do what time. And I can't zero in on those lab times. Actually, I'll probably have a broad range of them, but so watch for more things coming in the next day or so, and keep up on things. So if there are no questions, I'll stop sharing and end the meeting here.